Welcome back. Have you ever wondered? We see a lot of animals with camouflage or objects with similar colors to their background, but we are able to discern them from their background. Of course, we can do this when there is a large contrast change between the background and the element in front of it, like an orange colored bag in front of a black background. That's easy, right? But we can also look at like an orange colored bag and like against a slightly darkly colored orange wall. The question is, how can our eyes adapt to do both, and how can we give robots the superpower to do the same? In the world of adaptive edge detection, we will study today's concept called Canny Edge Detection. And this is one of the most important things in the field of computer vision. In the previous video, we were talking about how we can do edge detection using numerical gradients, but the problem we suffered there was that we had to manually carefully pick the threshold value to be able to know, okay, hey, do we want to get the texture of the cylinder, or do we want to get the texture of the background versus the cylinder, right? And if you have not watched that video, I would highly recommend and urge you to go watch that video, and it's pointed at the link here on the top. So let's recall our best friend Lena from before, and we are going to use her image to basically find edges in the image, and we will find weaker edges like the ones on the feathers and the hairs, but we will also find stronger edges like the hat with respect to the background and our eyes with respect to the skin and so on. This is the work of Professor John Canny, who is a professor at UC Berkeley right now, and this is one of the most influential and pivotal papers in the field of computer vision, which essentially tells you how we can do edge detection with both weak and strong edges automatically. And I would say it's automagically because it works like magic. So let's do this. This has multiple steps. In the first step, we will compute gradients. In the previous case, we used a simple Sobel detector. The Sobel detector is pretty noisy. So instead, we will use something called a difference of Gaussian operator. The idea is that this is like the Sobel operator with an added Gaussian blur. So it removes a little bit of the noise and then does edges on top of that. And if you remember from before, the gradients here are much smoother than what we had seen before. This is the gradient in X. Again, the whiter colors are basically positive values. The darker colors are black is basically negative values, and which is anything that is gray is basically close to 0. Again, remember that it's a signed quantity in this case. And we have the same thing for gradients in Y. And in the X gradients, you see mostly horizontal stuff, and in the Y gradients, you see mostly vertical stuff. Great. So in the second stage, we will compute the gradient magnitude. We will combine these two things using simple L1 norm, which is the sum of absolute differences or the sum of square root of the sum of squares. We can do either of them. And we will compute the magnitude, and the magnitude looks a lot sharper. Again, remember that in this particular case, we only have positive values because we have taken either the absolute or the square, right? And we went from something which looks like had negative and positive values and the gray value was 0 to something where black is 0 and white is positive. And the more positive it is, the more likely that it is an edge. Great. We also want to compute the orientation of the edges. The orientation of the edges is computed as the tan inverse of the ratios of the gradient value in Y to that of the X. And if I sort of plot that angle as a color code, which goes from blue to red with yellow in the middle, you'll go from negative to positive values, as you would see here. And I'm going to call this matrix the angle matrix. Remember that this has sub-pixel sub-angle accuracy, wherein sub-degree accuracy, but we really don't care about it as much. Remember that this angle matrix has sub-angle accuracy to the 10th of the degree or something smaller than that. But we don't really need so much accuracy in the angle. We don't really care so much because when we implement this, it's not that big of a deal, right? Instead, what we will do is we will quantize this to let's say every 22.5 degrees or every 45 degrees. And the angle matrix is going to look something like this, where it only has a certain set of colors rather than a lot of colors like we saw before. And just to compare, we had the angle matrix on the left, which is the raw angle matrix, and this the angle matrix A dash on the right side is basically the quantized version, and we are going to use the quantized version moving forward in time. So next, what we will do is we took Lena, and what we want to do is we have our edge matrix, and we basically want to detect the local maxima. So if we simply like threshold the values, you will see that only the stronger edges remain, and it's the same exact problem we had with the Sobel operator, though it's a little less noisy, but we still have the same problem wherein there is no connection between the things on the hat. For example, if you look at here, like the detection on the hat is very strong, but here as we get along, it's pretty weak. So the edge actually might be lost depending on the threshold, and we definitely lost the bow on her hat here, right? Great. So let's see how we can do this automatically. So imagine you have an edge running through the image. This is your white color edge, and the thing on the black is basically not an edge. And we take discrete values of the pixels, and which is denoted by these orange values. What we essentially want to do is we have the orientation and magnitude at every point. We take the orientation, which is drawn by these yellow lines across these red dots, and these red dots are basically wherever it's on the edge. So you take values which are on the edge, and what you do is you go on, depending on the orientation, you go on either side of the edge, and you look if the values of the gradient is actually higher than the red value, right? If it is, that is not an edge. If it is not, that is an edge. So this will essentially give us a denoised version where we are only left with these points wherein the gradient magnitudes is highest at the red point and it's actually lower around it, right? Which is great, and that's your sort of local maxima, right? And what we do is essentially we keep doing this, and we essentially want to be left with an edge thickness of 1, right? Edge cannot be thicker than 1 pixel. So what we want to do is we want to figure out a way to like make the edge thickness 1. So what we will do is at each of these red pixels which were remaining in the previous step, we basically go along the direction of the edge, not normal to the direction of the edge, and we will say basically, hey, like, is this an edge, right? And we keep maintaining this, and this is what it's going to look like. And this is called the non-max suppression, and this is a simple example of how this works as we saw in the top image. Then what we want to do is we found edges, but the catch is whenever it's a strong edge, this is fine, this works really well, this is easy, right? But the problem is the moment you encounter an edge which like sort of terminates at a point, you want to see if we can actually, if it's actually not an edge or is it a weaker edge, right? That's what we want to figure out. And this is called edge linking, and we are going to use this amazing mathematical concept called hysteresis. So remember that we are starting with a strong edge, we are going along the tangential direction of the edge, and we end up with this pixel here wherein like you say like, hey, I don't see the edge anymore. Again, remember this is with some threshold, so we might not see it. If you saw this from a zoomed out view, you might see something like that, and as a human being you might be like, hey, I need to connect these two edges with something, right? But we want the algorithm to figure out that this is a weaker edge in the middle, right? Essentially we want to adaptively switch thresholds so that we know that the edge can continue. So what we will do is we will start with a very high threshold to start at the edge curves, keep going on doing this on the ANMS non-max suppression output from before, and then at a point where we attain a juncture wherein we say, hey, like, is this an edge or not, we will drop the threshold to something lower. And again, this is a prefixed amount, and we notice if it is an edge at the lower threshold. If it is, we continue with the threshold and keep doing that again until we encounter a higher threshold edge, wherein we go back to the higher threshold and continue doing this back and forth, right? So this essentially lets you switch between a higher threshold and a lower threshold. It's like the best world of what we were doing with the Sobel edge detector, but we are automatically figuring this out using an algorithm. And this lets you do what is called a hysteresis, which is like a double-ended, like low and high threshold operator, which lets you start with the high threshold edge or a strong edge, and it lets you continue the curve to a weak edge, because just taking simple weak edges might give you a lot of noise. So you know that when it's starting from a strong edge, the weak edge is actually a valid edge, right? Awesome. So one of the best things in the paper of Canny Edge Detection is that he came up with this thing called the optimal edge detector, or the optimal robust step detector, which is If you have an edge, you basically want to see a step function. But the problem is that there is a lot of noise, right? And he came up with a mathematical formulation for detecting this in an optimal manner. When you actually derive this is very, very, very complicated, right? And this equation is one of the equations which feeds into the previous few equations, and it's very slow to run this stuff. And I think the best part of the paper is that Canny did not stop there. He essentially said that this almost looks like a difference of Gaussian as we saw before, right? And that simple approximation with the shape being almost similar. The top is the original optimal stepped edge detector. The bottom is the first derivative of a Gaussian, which is a Gaussian kernel and a Sobel kernel like convolved together, right? Which is essentially a Gaussian kernel and the Sobel kernel convolved with each other. You see that is a very simple operation. It can be computed very, very quickly, but it almost gives you the same thing as this optimal step detector, right? And that's the most beautiful thing in this paper. So this is great. And if you use this if you use this difference of Gaussian operator or the optimal operator and do the steps we talked about, wherein you start with the non-max suppression, then you basically use the angles and the quantized angles to move along around that edge, and then you basically, like, wherever you encounter the stop of this strong edge, you continue with a weaker edge and you do linking, you get beautiful edges, right? And that's what we saw. So now let's look at how the outputs look like for the Sobel edge detector from the previous video. If you haven't watched that, I would urge you to watch that, and the Canny Edge detector we just learned. With the Sobel edge detector, basically if you pick a very low threshold like 0.01, you see a lot of edges, which is very noisy. You see a lot of noise as well. If you dial it right in, it kind of works pretty decently well, like at 0.05, but the problem is you have to dial this in for every single image, and it's pretty painful, right? If you are a little off, like 0.1 here, you lose a lot of the important features like the face and the background and the feathers and so on. But if you look at the Canny Edge detector with its amazing automatic adaptive thresholds, it is pretty much perfect in the first go, right? And that's what makes this one of the most useful tools in the field of computer vision today. So in the era of computer vision with deep learning, how do you actually get data to do this with a deep neural network? What you would do essentially is you would ask a lot of people basically to manually draw edges over this image. For example, both I and you might have a very different description of what an edge is. The question is, how do you deal with something like that, right? And if I were to draw this, you could see something like this. The problem is that because it's so noisy when we do this with different people, it's hard. So the solution is that you ask a few people, let's say 5 or 10 people, to do the same thing for this image, and then you basically look at the overlapping edges between multiple people and you use that consensus to essentially train the algorithm. And your algorithm could predict something like this, right? And this is one of the papers called DexyNed. It's an older paper from 2020, about 5 years ago, wherein it uses a unit style architecture to basically predict the edge map probability given an input image. The question is there bias? The most definite answer is yes. It depends on the way you would label it, because when multiple people label it, they label it very differently, right? Depending on where these people come from, they might give different importance to what they are trying to say. And depending on the way the prompt is given, if you say the prompt is, tell me what is important for driving, that would be very different from just saying, hey, I want to use this for a sketching or coloring book, like make the edges here, right? It could be very different. So, and that's what we're seeing here. The biggest problem is we don't know what these edges are. These could be semantic edges, wherein the edges could be from one object to the other. They could be specific object boundaries, wherein subparts of the objects are boundaries are determined, or it could just be changes in color, right? So the coolest thing about this entire thing is that you can make your own coloring book given an image. Take any image you want, basically run it through a Canny Edge detector or some neural network based edge detector like this DexyNed, and you have your own coloring book algorithm which you can make for your kids. It's going to be a highly personalized gift, and it's super fun to actually play with this stuff. You can use edges for filtering. Basically, you can use edges to continue doing how we were doing the barrel detection like before. So be creative, keep your eyes open for the world of edges around you. Hopefully you will see edges in the real world and have a little more appreciation towards these edges and how we can give our robots this amazing property of edge detection from now on. So with this video, you should be able to understand why we need dynamic thresholds for edges, why this is so hard, and like how Canny Edge Detection actually can do this with 4 different steps. And we also should be able to say how does Canny Edge Detector handle both strong and weak edges, and how you would implement edge detection using neural networks in today's day and era. See you next time. Take care. Bye-bye.